When it comes to electronic circuit testing, especially any sort of power-related device, one of the most common pieces of equipment in use will be some form of electronic load. Usually this is a constant current load, but other electrical parameters can be stabilized as well. Hello, and welcome back. Today I want to look at how the main types of active loads work and how they can be built. We will be analyzing the more common constant current load, but also the less used but still important constant voltage and constant resistance load. So if you're curious about how these work, then keep watching. So let's start things off with how an active load is actually supposed to work. The basic circuit is usually a two-terminal device with some sort of regulating element, a power transistor, which adjusts the flow of current. The exact type of load will be determined by how the driving signal is created. For the basic constant current load, you monitor the current running through the circuit and compare this to a reference. The actual current measurement is usually done using a shunt resistor. Based on the difference between the reference and the measured value, you drive the regulating element, which stabilizes the current. Now, for the constant voltage load, it's more or less the same thing, but this time we monitor the voltage present on the terminals. The voltage that is being stabilized will be larger than the reference, so that is why a divider is usually needed. Now, for the other types of load, you need to combine the first basic ones. So you can make a constant power load by multiplying the current and voltage information. There are analog multipliers out there, but this is just a complex circuit that is easier built when using digital electronics. So I will not be analyzing this in too much detail today. But a constant resistance circuit is a far simpler design. You still take the voltage and current measurements performed in the same way as for the base active loads, but to maintain a constant ratio, you just need to compare the two. No more reference voltage or other mathematical operation is needed to do this. Now, to illustrate this operation, I first made a set of simplified test circuits. So here I used an ideal op-amp, a random transistor from the library, and the bare minimum of supplies. So starting off with the constant current source, the way in which you set the current is by matching the voltage drop that is occurring on the shunt resistor with the voltage coming out of your reference. In this case, for the reference, I used a voltage pulse that goes from 0 to 0.1 volts. So this, combined with the 100 milliohm shunt, should equal a maximum current of 1 ampere. So if we run and check this, and we look at the current running through our circuit, this is indeed what happens. We start off at around 0 amperes and finish at around 1 ampere. Now, before moving on, it's important to notice that while this circuit does work as expected, you need a very small reference voltage and a relatively large shunt resistor. The larger the reference voltage will be, the more voltage needs to drop on the shunt resistor. And usually, you want to minimize this. I mean, to make the circuit more robust, you can either increase the voltage drop on the shunt, which in turn will increase power dissipation, or you will need to use some sort of filtration methods to reduce the noise present in the circuit. If this is a more severe problem though, you can always add in an extra op-amp to amplify the voltage that is present on the shunt. So this allows the usage of either a larger reference voltage or a smaller shunt resistor. But the downside of this method is that this will bring extra phase shift and complexity into the loop. So the strategy is not always advised. Anyway, moving on to the constant voltage source, I used a similar set of components, but there was one important change. I had to use a resistor in series with a supply just to see the voltage to which the active load ends up stabilizing to. Now, if we look at the output of the circuit, there seems to be some sort of issue right at the beginning, so the load doesn't stabilize from 0, but rather from around 0.6 volts, and this is to be expected since the transistor that I used has a non-zero collector-emitter saturation voltage. So this might have been a bit better with a MOSFET, but to some extent you will still have this issue. But anyway, after this point, the voltage set by the load and the voltage on the reference do seem to be in agreement. Now, in both these cases, The common way of adjusting the load parameter is by changing the value of the reference voltage. Or at least for the constant voltage source, you could adjust the resistor ratio. So with the current load, it's usually not practical to adjust the shunt value. But finally, if we move on to the constant resistance load, this is a combination of the previous two circuits. The equivalent resistance presented by the circuit is determined based on our free resistors. And in this case, so with the set of values, it's about 10 ohms. So to test out this circuit, I set the supply voltage to have a rising ramp. And if we check the voltage present at the terminals, as well as the current, both seem to be rising at more or less the same rate. But we can of course verify just how well the supply is regulating the resistance by dividing the two. So when we plot out this quantity, we can see that we are getting a relatively stable 10.1, 10.2 ohms. So the circuit is regulating the resistance. So all in all, any of these circuits should work just fine in the real world, though they will need a few more components. Today's video is sponsored by GLC PCB. They provide easy, affordable, and reliable PCB and PCBA solutions, empowering electronics engineers to develop projects efficiently. For today's project, I will be using a set of aluminum substrate boards which have improved heat dissipation capabilities, and combine this with a set of stencils that help to easily deposit solder paste. These boards will be used to make the active boards we will later test. Ordering a set of boards is as easy as dragging your Gerber files onto their website and setting a few configurations. Up to 8-layer boards can be obtained for as little as $2, and you can get a $30 coupon for the 6-layer boards. So even larger PCB sizes can be obtained for only $5. Easy to use, affordable to make, and reliable. Check out the link in the description for more details. Whenever building a practical device, other than the functional, there are always some more aspects to keep in mind to make the circuit actually usable. On the one hand, you want to minimize the number of external equipment needed to get the circuit to work. On the other hand, whenever a human is involved, mistakes will be made. So first off, the simulations use three supplies: the reference, the IC supply, and the load. While in some cases you want an external signal to make the active load variable, if you just want a static parameter, the first simplification that can be done is to take the reference voltage out of the supply. Usually the supply is stable enough to act as a reference. Maybe just a resistor divider can be added. The second important simplification that can be done has to do with knowing the load voltage. As long as this is always above a few volts, you can simply take a small LDO and power the circuit from the load itself. So in the final build, this is the way I chose to supply the board. Now, taking this approach does bring a few limitations. I mean, you want the circuit to work at lowest possible load voltages. So to determine this minimal operating voltage, as well as to keep it as low as possible, requires a few measures. First, the LDO needs to be as low dropout as possible. Second, the operational amplifier needs to be in its normal operating range, so you need a low voltage type op amp and preferably a rail-to-rail one as well. This keeps the input and output voltage swing as close as possible to the supply rails. Finally, the power transistor needs to be able to operate at low control voltages, so it can be made bipolar, and to keep the strain on the op amp minimal, it can be a compound 2-transistor structure. We could use a Darlington pair, but this would require a roughly 1.4 volt minimum control signal. Alternatively, we can go for a cycloid pair where the control is halved. And finally, in case a shunt resistor is present, the maximum voltage drop on this component needs to be considered. So the minimum supply voltage will either be a sum of all of these, or it will be imposed by the op amp's minimum operating voltage. So in other words, it shouldn't be all that difficult to get such a circuit to operate as low as 2 volts. To confirm the strategy, I first built the circuits in the simulator using realistic component models. So for the op amp, I went with the MCP 6001, a rail-to-rail op-amp that accepts a minimum supply voltage of 1.8 volts, and for the transistors, I used a couple generic components that I had lying around. So other than the components already discussed, the additions appearing in these schematics are the resistors around the transistor assembly, and there's an extra capacitor that is used to limit the op-amp's slew rate. So this is not a mandatory component in the simulator, but rather something that should help prevent oscillations in real life. So if we first check our constant current load, we can see that it is stabilizing the current at the 1 ampere point, so the output of the op-amp is well within its normal operating range. And even though the voltage does change from 2 up to 20 volts, the current changes by a very small amount. Next, we can have a look at the constant voltage load. So here, a variable voltage is supplied through a resistor, and we can check that the voltage present at the terminals of our circuit does indeed stay stable, even though the current is ever increasing. So again, there's no issue here. Finally, we can have a look at the constant resistance load. So here we can see the rising input voltage, rising input current, so both seem to be proportional. But to get the right value, we can of course divide the voltage by the current and get our stabilized resistance. So again, it's not perfect, but we are very close to the set value of around 22 ohms. So in essence, all three of these circuits should work just fine. Now, for the final build, I did make a few more tweaks to the schematic. On the one hand, the set parameter should be adjustable. On the other, the device should be human-proofed. So let's start with the constant current load. So I used a 3.3 volt LDO in all of the schematics. The 1.8 volt version was not in stock. And then I also added in a basic indicator LED, just to show that the circuit is powered. Now, it is true that the LED supplied at 1.8 volts would have difficulty turning on. But anyway. Now, at the right side we have our connector, and here there are two noteworthy elements to mention. So first, I left room for a RC snubber. This can be helpful if the circuit is driving long wires, so this should suppress oscillations to some extent at least. Now, I did not assemble this, but it is foreseen. And the second thing to mention is a Zener diode, which serves two purposes. On the one hand, if you're correctly supplying the circuit with a too large of a voltage, larger than the diode rating, then the diode will start conducting and protect the circuit from exposure to overvoltages. And second, if a reverse voltage is applied, again the diode will conduct, preventing a reverse voltage destroying the circuit. Now, adding in a fuse, maybe even a polyfuse, would have been quite helpful here. But even so, these two elements should protect the circuit from most of the cases of mishandling. Now, moving on to the constant voltage load, here there are two other things to mention. So first, you need to set a low limit to the adjustable element. So when this is reached, you need to ensure that there is still a minimum voltage available for the circuit to actually run. And the second thing has to do with the feedback capacitor. So here I used the 47 nanofarad capacitor, since with a practical board, I did have some stability issues. But to be honest, I'm not yet convinced if the issue was the capacitor or some sort of faulty solder joints. But anyway, like this, everything seemed to work just fine. And finally, looking at the constant resistance load, there is nothing really special compared to the previous circuits. You can set a minimal resistance value using these two components, but for the maximum, there is no limit really imposed by the trimming potentiometer, only maybe by the total consumption of the unit. Now, the last thing to mention about this design is that I wanted to build it a bit differently from my previous active loads. So I did build active loads in the past, usually current loads. I also covered one of these in more detail in an older video. But the main difference between those and today's build has to do with how the power transistor is cooled. So the typical way to go about this is to have some sort of through-hole large power transistor screwed onto a heatsink. You either connect this to the main board with wires, or you need to make sure that the holes in between the board, heatsink, and transistor are all aligned. But what if you didn't have to separate the board from the power transistor and heatsink, and could just bring everything together? So the special thing I wanted to try on this build is to use aluminum substrate boards to contain both the driving circuit and the power transistor, and then to dissipate the power through the board to a heatsink. You could do this with a normal FR4 board and a bunch of thermal vias, but aluminum is far better at this. It's quite a common practice in lighting fixtures, but it also does come with the downside that the layout typically needs to be a single layer. Fortunately though, since this is quite a simple design, everything did end up fitting into a single layer. There are no tricks or anything used to interconnect the components. So this is the constant current load, but all of the designs are very similar to this. Now, in case it would have been needed, you could have used a 0 ohm resistor or jumper to jump over some of the traces. But anyway, not much to say about this design, other than the main power transistor is right in the middle of the board to maximize heat transfer, and then everything else is to the sides. So the left side contains the connector and the input protection elements, the top side contains the LDO and the indicator LED, the right side contains the op-amp and the trimming potentiometer, and for two of the three boards, the bottom side also contains the shunt resistor. So that's basically how these were designed. Now, assembling aluminum substrate boards under industrial conditions is not an issue, but for the hobbyists, it can be quite difficult. The aluminum is highly heat conductive, so any soldering becomes very difficult. For this reason, I also got a stencil, and after a bit of struggling, I got the board aligned with the holes. To keep it in place, I did use some masking tape. Anyway, afterwards, I tried to apply some solder paste. And try I did. The issue was that the paste I had was opened years ago, and it wasn't really stored in appropriate conditions, so it got quite dry. Anyway, once the paste was applied and components were placed on top, it was time to somehow melt the paste. For this, I used a rather unconventional technique which I cannot really recommend. It's not that great. And you still need to combine it with some hot air. Regardless, the boards were assembled one way or another. Now, the nice thing about such a substrate is that if you have small power dissipations, you can just use it as is, or for larger power levels, you just assemble this to a heatsink. However, regardless of the assembly method, there is no separation in the electronic circuit. It's just one piece, so it's far easier to assemble, and it's more robust than if the components would have been separated. Now, after a short set of tests, I can confirm that all of the circuits do operate. So here I connected the constant voltage circuit through a resistor to the power supply, and while I'm varying the voltage on the supply, the voltage present on the active load is fixed. Next, I tried the constant current sink with variable levels of input voltage, and this setup was used without any extra heatsinks. So while this does work, as the board, especially the shunt resistor, gets heated up, the current did end up varying quite a bit, so the exact value was temperature dependent. This was probably the case with all of the other boards to some extent, but here it was far more obvious. Anyway, for the constant resistance load, I first used a heatsink to stabilize it, and to measure it, I used both a voltmeter and an ammeter, and proceeded to make measurements at multiple voltage points. Now, just to confirm the operation, I performed a set of calculations highlighting the equivalent resistance. So the circuit as well also seems to work just fine. Now, I had no doubt that the circuits would work. Other than a bad solder joint, the circuits in principle should operate quite reliably, especially when making a static load. They can be temperature sensitive to some extent, but it's not that bad. However, the thing I was most curious about though was the thermal behavior. How well does an aluminum board actually transfer heat? So first, I applied some paint, which some might call nail polish, but I say it provides high emissivity and makes the transistor look fabulous. So first, to test the constant voltage load, I set it to dissipate around 6.8 watts. I let it run like this for a while, until the heatsink temperature stabilized, and then took some infrared pictures. So from afar, it seems that the board and heatsink are running the same temperature. Other than the transistor hotspot, it all seems to be quite uniform. However, on a closer inspection, we can see that there is indeed a bit of temperature difference between the transistor pad and the area around it. So we are getting about 10 to 15 degrees of difference, indicating that the thermal resistance is somewhere in the 2 Kelvin per watt range. For the board without a heatsink, I set a lower 2 watts of power dissipation, just to prevent any accidental overheating. Here again, we can see a similar story. The aluminum substrate does provide a good temperature uniformization, so other than the transistor hotspot, there's no gradient really visible. When zooming in, we see a similar heat spread coming from the transistor. The immediate area is hotter, but then it just reaches the same temperature as the rest of the board. So, based on the temperature difference and the power dissipation, we're in the similar 1 to 2 Kelvin per watt range. In the end, building active loads is not all that difficult. But as with any design, the devil lies in the details. To get a reliable device, you need to not just worry about the thermal heat dissipation, but also keeping the parameters stable during operation. While the aluminum substrate will help with the heat issues, keeping the references and measurement elements in their normal operating range is a completely different aspect. So with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.